Okay, so 4.4 talks about what we call intermolecular forces. Now, the prefix inter, INTER, that means between. So intermolecular forces mean forces that occur between different molecules. Okay. When we talk about like our covalent bonds and our ionic bonds, those types of bonds are intramolecular. Um, and so intra means within. So if I'm talking about an ionic bond or a covalent bond, that's an intramolecular force because it's inside, it's within a molecule or a compound. Inter is going to be between two or more molecules. Okay. So what we're going to do is we're going to talk about there's different types of intermolecular forces, and each one of them has some specific strengths and some specific ways that they affect some of the physical properties of substances. And so this kind of we're going to talk kind of a little bit about why certain substances, will dissolve and some won't, why some can feel electricity and some won't, and things like that. And it has to do specifically with their chemical structure, and whether or not they have intermolecular forces. And it all goes back to figuring out if the molecule is polar or nonpolar. Okay, that's the biggest thing. You need to be able to draw the Lewis structure, look at the bonds in the molecule, and figure out if the molecule as a whole is polar or nonpolar. Because polar molecules can have some of these intermolecular forces, and nonpolar cannot have some of them. And so, if you can't do that, then it's going to be hard to identify what type of intermolecular forces a specific molecule would be able to have. So, as I said, we're going to outline the formation of the three types of intermolecular forces. We're going to talk about how they're different. We're going to talk about what features of a molecule. So, as I mentioned, sort of the polarity of the types of bonds and things that are in it, how that determines the type of intermolecular forces that molecules can have. And then we're going to explain how the physical properties of covalent compounds, specifically volatility, electrical conductivity, and solubility, how they're affected based on, or how they're changed based on the type of intermolecular force that a particular molecules would have. All right, so as I said, intermolecular forces, they're forces of attraction, they're in between molecules. The three types we're going to talk about, there are London dispersion forces, there are dipole-dipole forces, and then the last one has kind of a different name. It's called hydrogen bonding. So the first two, there's some sort of forces. The last one's called hydrogen bonding, but it's kind of a I don't want to say, it's not a wrong name, but it's kind of like a misleading name because it makes you think of like covalent bonding and ionic bonding, which are inside the molecule. And hydrogen bonding is not a chemical bond. It's not holding some two atoms together inside a molecule. It's still an intermolecular force. It just happens to occur between hydrogen and some specific elements, and so they gave it the name hydrogen bonding. Okay. Um, London dispersion forces and dipole-dipole forces, we can kind of group them together, and collectively we call them van der Waals forces. Okay. So London dispersion forces, we're going to talk about first. All covalent molecules have London dispersion forces. I'm going to say that again. All covalent molecules have these. Okay. It doesn't matter if it's polar or nonpolar, all of them have this. And the reason that all of them have this is what causes it. Okay. This causes, so it says right here, all atoms or molecules, both polar and nonpolar. The reason that all of them have it is because this is due to the motion of electrons, and all of our atoms and molecules have electrons. That's what allows them to bond together. Okay. And so it's caused by the constant motion. We know the electrons are outside of the nucleus, they're constantly moving, they move really, really fast. And so what happens is sometimes maybe some of the more of the electrons are on one side of the atom or molecule than another. Okay. They're not always evenly spaced apart. And so what happens is they're moving so fast that sometimes one side of our atom or molecule is going to have a partial negative charge, and the other side is going to have a partial positive charge because this side over here there's more electrons concentrated over here at that instantaneous, at that one like split second in time. And so a lot of times we will call um, London dispersion forces, we will say that they cause what's called a temporary or an instantaneous dipole. So temporary dipole or instantaneous dipole. And that just means that it's only there for like, you know, I don't know, a millisecond and then it's gone. Okay. And so what happens though is for that like, you know, really short instantaneous time that that dipole is there, um, it can cause a nearby molecule to have what we call an induced dipole. So um, it's kind of like this instantaneous dipole is kind of like the, you know, the bad influence, and this is their friend. And because they have this side that's slightly negative and the side that's slightly positive, and they're nearby this other molecule, it causes this molecule to have a dipole, instantaneous dipole as well. But it's induced because it was caused by the first molecule. Okay. So it's kind of like the one that gets the instantaneous dipole, it's going to influence all the molecules that it's nearby and cause them to have an induced dipole. And so that causes it's sort of kind of like a chain reaction, because then if there, you know, if there was another molecule over here, you know, maybe it would also have another induced one and it would be, you know, negative and positive. And so it can kind of keep going, and it can cause several of the atoms or molecules to do this in a sample of a substance. Okay. I want to just go back up here really quick and just say that London dispersion forces, these are the weakest type of intermolecular force. They're the weakest because they're only due to the motion of electrons and they're temporary. Okay, so that's why they're the weakest. They do have a significant effect though on the physical properties, like things like boiling point. Okay, and when we get to done talking about all three of these, we're going to compare them and we're going to see, you know, how they affect them. But they can affect the boiling point, because what happens is the higher your molar mass. Okay, that more molar mass means you have more protons and electrons in your atoms, correct? So what that means, more electrons means that you're going to have more of these instantaneous and induced dipoles. And so the more of these you have, the more that's going to affect something like your boiling point or your melting point. So typically on the periodic table, if we're comparing, you know, different elements, we would say that, you know, ones with more heavier molar mass are going to have more of London dispersion forces, and they're going to have more of this effect on them. And so here is what I was talking about. Okay. Here's the halogens. This is the one that they like to ask about because they're all similar in this group with their properties. Fluorine is a gas in its natural state, in room temperature. Chlorine is also a gas. Bromine is a liquid and iodine's a solid. Okay. The reason that their states of matter change as you go down the group is because of this intermolecular force. Because if you look, the molar mass as you go down, the molar mass is increasing. That makes the boiling point increase. Okay. So they increase as the molar mass increase. And the reason the molar mass causes that increase is because, as I said just a second ago, if you have a heavier molar mass, that means that you're going to have stronger London dispersion forces, because you're going to have more electrons in order creating these instantaneous dipoles. So, you know, larger molar mass means there's more electrons that can cause these instantaneous dipoles, and that increases the strength of the London dispersion forces, which makes it harder to change from a gas or from a solid to a liquid to a gas. So that's why at room temperature, the halogens kind of change state as you go down the group from gases to liquid, eventually to solid. Because the one is at the bottom, like iodine, they have stronger London dispersion forces. So it's a higher boiling point because it requires more energy to overcome the attractive forces between the molecules. There's more London dispersion forces in iodine than there is in bromine, and then chlorine, and then fluorine. Okay, so our second one is the dipole-dipole forces. This is the one's kind of in the middle. It's stronger than the London dispersion forces, but it's not as strong as the last one. We're going to talk about the hydrogen bonding. So it's the second strongest. Okay. This one occurs between polar molecules only. So if you identify a molecule as nonpolar, there is no way, it is not possible for it to have dipole-dipole forces. Nonpolar molecules only have the London dispersion forces, and that's it. Okay. If you have a polar molecule, it's going to have London dispersion forces still, but it's also on top of that going to have dipole-dipole forces. Okay. So dipole-dipole forces happen when you have polar molecules, because what happens is we talked about that polar molecules is where one side of the molecule is slightly positive, like this hydrogen in this one, and the other side is slightly negative. So this is a dipole. It's not instantaneous though. This is a permanent dipole. We know that when we bond hydrogen and chlorine, chlorine has the much higher electronegativity. So the side of the molecule where chlorine is going to be partially negative, and the side where hydrogen is partially positive. And so because of that, there's an electrostatic attraction between the positive and negative dipoles. So if I have this molecule of HCl and I put it nearby another molecule of HCl, they're going to arrange themselves so that the negative side of one is next to the positive side of another. And then here's, a third one over here. And so it's doing the same thing. So this little dashed line right here, that is the dipole-dipole force, or the dipole-dipole attraction. And so a lot of times you'll see intermolecular forces represented with dashed or dotted lines like this, because they're trying to indicate to you that it's not as strong as this covalent bond. Okay, the covalent bond's a solid line because that's an intramolecular force. Things like dipole-dipole, London dispersion, and hydrogen bonding, they're not as strong as that covalent bond. And so usually they'll be represented by a dashed or a dotted line like that. Okay. All right, so the third type, hydrogen bonding. This is the strongest type of intermolecular force, and it occurs, number one, you have to have hydrogen, but it has to come in contact with one of three other elements. It has to come in contact with nitrogen, oxygen, or fluorine on another molecule. And so the three most common examples you need to know about are these three: water, ammonia. Okay, so this is ammonia, ammonia, if you don't know how to spell it. Water, ammonia, and then hydrogen fluoride. Because all these molecules have a hydrogen and they all have oxygen, nitrogen, or fluorine. Okay. And so what happens here is it's kind of similar to the dipole-dipole. You'll have the positive end of one molecule and it will line up and connect to the negative end of another. And we can see they kind of represented it similar with that dashed line. Okay. What makes these different though is the difference in electronegativity. Okay. Hydrogen compared to oxygen, and then hydrogen compared to nitrogen, and hydrogen compared to fluorine. Their electronegativity difference is it's a lot greater. Okay. And so these three types of bonds, or not three types of bonds, but these three between hydrogen, oxygen, hydrogen, nitrogen, and hydrogen fluorine, we give them this special category of hydrogen bonding. Okay. And so hydrogen bonding is the strongest one. And so molecules that have hydrogen bonding are going to have like really high melting and boiling points and things like that. And so this explains why water has such a high boiling point, because water has hydrogen bonding because it has hydrogen and oxygen in its molecule and it's polar. Okay. And so any molecule, so all three of these molecules up here, they still have London dispersion forces because all the molecules have London dispersion. And then they don't have dipole-dipole, they have hydrogen bonds. And so that's what makes them have the strongest intermolecular forces, and therefore sort of the highest boiling and melting points, as because it's going to take a lot more energy to overcome these hydrogen bonds and break the water molecules apart. And so water molecules, it melts, and then to get it to boil from a liquid to a gas, you have to heat it up to a very high temperature because you need a lot more energy. Okay. And so it's similar to a dipole-dipole in that the hydrogen bond, it's going to have the positive dipole from the hydrogen atom, and it's going to pair up to the negative dipole on, in this case for water, the oxygen atom. And if it was ammonia or hydrogen fluoride, it would be the nitrogen or the fluorine atom. Okay. And so water is actually a very small molecule. Its molar mass is only 18.02 grams. So it's a pretty light molecule compared to a lot of other covalent molecules, but it has a much higher boiling point. Most of the time, things that are going to have smaller masses, they're not going to have very high boiling points, because they're so small. So they don't have a lot of those London dispersion forces. But because water has these hydrogen bonds on top of the London dispersion forces it has, that causes its boiling point to be very, very high. Okay. So this graph is kind of showing what I just mentioned. So this is comparing two groups on the periodic table. It's comparing the boiling points of hydrides. So those are elements that have been bonded to create a compound with hydrogen. And it's comparing group 14 and group 16. So let me switch colors really quick. So here I'm going to do group 14 first. So group 14, you have carbon in the second period, silicon in the third period, germanium in the fourth period, and then tin in the fifth period. So as I go kind of down my rows, carbon, silicon, germanium, tin, those are all in group 4. And notice the line, I mean, it's not exactly a straight line, but it's pretty close to just a straight line with a positive slope. There's not really anything, super out of the ordinary. It looks like they're just kind of each one's slightly increasing, which makes sense because all of these have the London dispersion forces. All of these are non-polar, okay? So all 4 of these that I've kind of written in purple, all 4 of them are non-polar. So that means that all they have is London dispersion forces. So it makes sense that as I go down the group, the boiling point is going to increase because their molar mass is increasing and they're following that trend based on the London dispersion forces. Now, if I come up here and I look at the trend for group 16. Now, here in period 3, period 4, and period 5, where it's sulfur, selenium, and tellurium, those are increasing like normal, okay, because they have the London dispersion forces, okay. The difference here is look where water is, okay. Water is in the second period. So, but look how much higher it is than the other 3. And so the explanation for this is because this is the only one that does hydrogen bonding. And so even though it has the lowest molar mass of all of these, it has the highest boiling point because the hydrogen bonding kind of supersedes molar mass, okay? So if something has hydrogen bonding, it's going to always have the highest of the properties like boiling point and melting point. If it has dipole-dipole, it'll be probably somewhere in the middle. If it has London dispersion forces, it'll be the lowest. And then if you're comparing compounds that only have London dispersion forces, the thing that's going to affect them is the molar mass. And so you're going to see it trend upward like this one or like these 3 in group 16. So the reason that that water kind of breaks that trend is because of the hydrogen bonding. All right, so on your exercises, I just lost the, hold on guys. So on your exercises here, it says like on number 2, identify the strongest type. Because remember, I told you that if something is a nonpolar molecule, this only thing it's going to have is London dispersion. But if you have a polar molecule, it'll still have London dispersion forces, but that won't be the strongest. It'll be either dipole-dipole, or if it's something with oxygen, nitrogen, or fluorine and a hydrogen, then it would be hydrogen bonding would be the strongest. Okay. So some of them can have more than one, but the strongest one is the one that it wants you to list for that one. Okay. The explanation stuff, again, think about what we talked about, the difference between London dispersion forces, dipole-dipole, and hydrogen bonding and how that affects something like the boiling point. Okay. So that is it for today.